Okay, welcome to the session on presentations and modeling activities. And our presenter is Heather Loy, and she'll be talking about energized modeling in mechanical engineering, teaching students to develop system dynamics ODEs using energy concepts.
All right. Well, thank you, everybody. So as a little bit of a disclaimer, this is not so much about a specific activity, but it's just sort of how I have embedded this concept into the course to hopefully make it more fun and more exciting for my students. So I am a mechanical engineering professor at SUNY New Paltz. SUNY New Paltz is a fairly small liberal arts college. It's part of the SUNY, the State University of New York system. And so we have a very small division of engineering programs, mechanical, electrical, and computer engineering. And so this class is a class that is taught specifically for mechanical engineers. So it's required for all of our mechanical engineers. They usually take it at the end of their junior year or sometimes into their senior year. And so this course has 3 particular student outcomes. Those learning outcomes include being able to develop models of a dynamic physical system. So basically just being able to develop the fundamental models. Then they need to be able to know how to solve those differential equations, which we've developed. And then finally, they need to be able to evaluate and understand how a certain system is going to respond to different inputs. So the focus of this talk is really going to be kind of on how I sort of changed the way that I thought about setting up models in learning outcome 1. So this class now uses formally the formal textbook is this one here, System Dynamics. That's the required textbook. And that one they access through, it's a McGraw-Hill, so they access through their online platform. So they've got readings and activities and questions through that. So we use that quite a bit. But then I also have integrated these other 2 sources, this one here, which is called The Captains of Energy, and it is kind of a comic book view of system modeling. And then also this course pack basically that was set up by these 2 faculty members at Brigham Young. And so they both deal with systems in a slightly different way than the primary text does. And so it's really how these 2 texts deal with it that I'm going to talk about today. And so the Captains of Energy, their basic concept that they start with is that essentially all systems deal with how energy flows through a system, right? So they have this effort flow analogy. And so the harder it is for energy to flow through it, then the more effort that's going to need to be put in, it's going to change the flow rate. So this whole process of energy and how it flows through a system is embedded in this framework of these different characters that basically show up all over the place, allowing things to be done, but also causing trouble. And so that's sort of the way that they address it. Now, the way that this course pack that I talked about addresses the exact same principle, this principle of effort and flow, is basically by describing all of these different types of effort variables and flow variables, and by basically coming up with this corollary for every single one of the different types of systems that we're going to look at. And so this was really just formational for me when I started looking at things from this perspective. So the combination of kind of stumbling upon this course pack that described how they taught their class and the Captains of Energy book, because all of a sudden every single section of every unit in my course followed this same pattern. And there were these patterns that before that I had not had any understanding of, really. So I had taught the class for a year and was almost just kind of bumbling through almost just every chapter, trying to figure out the best way to teach the students related to that specific topic. But now all of a sudden there's this cohesive picture that we can use. So that's what I've started to do. So when the students come into class, I basically start by saying, look, this is, this is what modeling is, and these are the different types of systems that we're going to model. So all of these pictures that you see here, they all come straight from that traditional textbook that we're going to use. But I jump right in and I say, okay, we've got all these different physical systems, but guess what? They are all made up of elements that do one of three things. And those three things that they could do is either store energy due to position or potential energy, right? So that's our effort based. And right away I can say, hey, do you guys remember in your physics class, what do what's potential energy? So they can connect right to that. And so then we basically say, okay, we're gonna use this little character. So this is the guy from that Captains of Energy. And I always encourage my students to buy the book because I think it's great to see kind of how they talk about it. But here's our energy guy that talks about this potential energy. And then we go on and we say, okay, now the energy can also be stored in terms of motion or flow based. Yeah, and here's all of our different elements that are potential energy storers. And then we have for flow based, same thing. Now we have this guy and he's got a little spring looking like thing on there because that relates to an inductor in an electrical system, right? And so he's storing energy due to motion as well. And so once again, we can identify, and I'll have the students all work together with me to identify which of these different elements show up here. You'll notice that in the thermal system, there is no kinetic energy storage, right? So that's an interesting thing. That's really the only difference between the three systems. And then finally, energy can be dissipated, right? And so that's our third character here. He's like the evil Mr. Resistor guy, and he's the one that comes in and actually takes away energy from the system. But then once again, right away, I can have the students from the very beginning of the class start to understand that there is going to be resistances in every single one. Now, this is really, really important because I found that students would get really confused between, what these different elements in a system would do before I had this framework. And even now a little bit, but a lot less. So for instance, I have people that would come up to me and say, well, a spring is basically like a resistor, right? And so a spring, as you can see from this chart, what does it do? It's going to store potential energy. A resistor is going to dissipate energy. So then I can say, well, they look similar on the drawings, but actually they have very different roles. And so now I can just show them, you can just show them this page, and all of a sudden they're able to see how actually a spring is like a capacitor, and then those little light bulbs can go off. And that's really sort of how, from there everything kind of goes from that perspective. As I say, okay, let's look at a specific type of system. So I'd start with mechanical systems, and so with a mechanical system, we've got all kinds of different ways that things can move, but actually we can think about the energy that's going on in them in, if we're looking specifically for kinetic energy, let's say, we can describe that kinetic energy as basically translating, energy due to rotating, or some of each, like we see here. And so then what you can do is you can actually distill it down to an equivalent, either an equivalent mass or an equivalent torque, that allows you to encompass all of the motion of this object in one number, right? And so like here, for instance, the equivalent mass of this whole cart includes the mass of the cart itself plus 3 times the mass of the 2 wheels that they have here, right? So then this becomes the equivalent mass. Another way that you can find equivalent masses is if you have distributed masses. So now you can take these distributed masses and you can use that to identify what the equivalent mass is. So as soon as you have this equivalent mass, then you can replace all of this complicated geometry that we saw before, whether it's a cantilever beam or it's a wheel that's rotating, you can replace it with an equivalent mass. And then that equivalent mass can be incorporated into your system. In the same way, we can do the same thing for springs. So if we have some type of a specific geometry where we have this distributed stiffness across it, we can actually identify what the equivalent stiffness would be. So once we know what the equivalent stiffness and the equivalent mass are, then we can put those together and we can come up with a system that doesn't actually look like this overly simplified system, but it actually behaves very similarly to that. So then at this point, we can also add damping into the system if we need to, and we can come up with a model. And so then at that point, I can show the students that there are basically, if you're talking about a single 1 degree of freedom spring mass damper, these are all of the possible different configurations that you could have. So if they know how to derive the dynamic equation that you see here for every single one of these, then they can basically tackle any problem that's a 1 degree of freedom spring mass damper. And so that kind of it starts to help them to be able to kind of wrap their mind around the fact that I'm asking them to be able to model all different kinds of systems, because all they have to do is be able to identify what part of this system is dissipating energy, what part of the system is storing the potential energy, and so on and so forth. And then the other thing that they can look at is where are the attachment points for these different types of elements that we have. So for instance, I'm going to come back up here to this guy here. So here we see this rack and pinion. Do you guys see that? It's rolling. So let's say that there was a frictional force between this rack that's sliding and the ground, right? So now they can identify that there is a damping that's basically between the moving mass and the ground. And then let's say that this shaft here is actually kind of compliant. So there's some stiffness in there, right? So all of a sudden they can take that and they can basically come back to here and they can say, okay, I've got a rotational input. And so I'm going to rotate that. It's got some stiffness. Then I've got my mass, which I've turned into an equivalent mass based on the rotation and the translation. And then I've got a damper, which goes from the mass to the ground. And so now this gives them this fairly straightforward mechanism for evaluating any type of mechanical system that I can show them a picture of. And they just simply have to begin to just very systematically just look at it, figure out what's actually moving, so where our masses are and what our different dynamic elements are. And so based on that, then it basically allows the modeling to become a much less of kind of a really scratching their head and not really knowing where to start, and much more of a systematic process. We could do the same thing in electrical circuits, right? So I usually start by saying, hey, how is an electrical system like a mechanical system? And then, we pull up our electrical circuit and we just go right back to those energy, different types of ways that energy can be transformed, right? So we figure out what our resistance or what our what's acting as a resistance in our mechanical system. And we can identify that the resistor is going to do the same thing in our electrical system. We have capacitance and we have inductance. And so in these three ways, we can figure out what is going to dissipate energy, what is going to be storing energy as potential or kinetic energy. And so this then provides that same type of framework for how they can analyze this. So then we can go in and we can build on that and say for each of these different elements, we have constitutive relations and integral causality. So we take those and that gives us these equations. Now, for my mechanical engineering students, this is where, they get nervous, right? They get nervous as soon as we start looking at something that's not just a mechanical system, but I can show them how they're going to develop it using essentially the same kinds of building blocks, and they can use that to develop their models. So armed with all of this information, they can then go in and we do our modeling both in the time domain. So here on the left-hand side, you see here's the time domain model. And then in the middle here, we also have a let's see if I can get this to work. There we go. Then in the middle here, we also have a frequency domain or Laplace domain analysis, and it can show them how in either case, you're going to end up with exactly the same dynamic model for this. So it's in terms of our second order differential equation. Okay, and once again, you'll see we always go right back to those different the different types of energy storage. So then next we can do the same thing, and we can basically say, hey, look, it worked for electrical circuits. You'd never seen anything quite like that before, and you did just fine. So let's take a look at how we can use this for our fluid systems as well. And then you can relate the same different types of systems once again. And then we can take a look at our different laws, and we can show how they relate directly to the fluid systems as they did with our electrical systems. And that then allows us to develop, once again, another set of differential equations. And so then we're back to the same place that we were with our electrical circuits, with our mechanical systems of there's going to be lots of different systems. They're going to have different components, but guess what? We can identify in each one of these, how many capacitive systems, how many capacitive elements are there? So for every capacitive element, that's going to increase the order of our differential equation. And they can systematically go through a problem. We can also identify what type of problem it is, right? So depending on whether it's a liquid level problem, like I just showed there, or it's a problem where instead of the height changing, right? So with these problems, we're just looking at how the height changes around its equilibrium point. We can also look at how the pressure changes in a pressurized tank. We can also look at how the mass is changing in a hydraulic piston. Okay, so we can take all of these are based on those same things, and they all tie right back into those different elements and how energy is being transformed. And so then finally, we've got our thermal systems as well. And so there I remind them of the fluid and the electrical systems. And then I also remind them that there is no inertial storage or kinetic energy. And so at that point, we can have a good conversation, right, about why is it that with fluid systems, electrical systems, mechanical systems, we always have this storage of energy due to motion, but now all of a sudden we don't have that anymore. Okay, and that can help spur students on to sort of a better understanding of just the nature of heat flow and, basically what's happening as you have a thermal system. And we can talk about how energy can be lost and energy can be stored, but it can't be, so it can be stored basically due to effort, due to the temperature gradients, but it can't really be stored due to motion because there's no mass corollary here. But we still have the laws that are very similar, so we can still use the conservation of heat energy, just like we use the conservation of energy in both of our fluid and electrical systems. And then that basically provides the framework for that type of modeling that we're going to do. So basically, once we've done that, so we spend probably about 2/3 of the class just simply going through all these different systems and learning how to model them. And then we really get to what I think is sort of the fun part, and that's where we actually start solving our ODEs, and we also begin looking at their behaviors, right? And so once again, at that point, I bring them back here and I say, look at what you've done so far, right? These are all systems. And at this point, they know, they can look at it and they can say that it's a first order differential equation. And, they understand the format and they can start to understand, what all of these different system parameters are, right? So by this point, they should be able to look at this and say, oh yeah, see, I know that relates to energy dissipation in this mass. And then they can come over here and say, oh yeah, so this tank, so that tank cross-sectional, or the sectional area there is going to be related to the amount or the capacity that this has for storing energy due to the fluid height. And then we can look at, oh, and then there's this resistance in this line, and maybe there's some inertance if the lines are really long. And they can start to identify, kind of refresh their memory and remember all of these different things that they had learned, and realize that every single one of these has essentially the same form. And then we can start talking about, based on those patterns, the fact that each one of these has a time constant, and we can establish what that time constant is based on the parameters of the system. And that's where we can start talking about the fact that every single first order model that we have for any of these systems is always going to be characterized by this time constant. And then that gives us a framework for, once again, being able to use the same tools to evaluate all of these different types of systems. So then we...
Heather?
Yes? Am I
You
out of time?
Yes, you got only 3 more minutes for the next speaker to start the presentation. If you could wrap up right now and ask questions, that would be great.
Sure. Let me do that. I was almost at the end of my slides, so let me just go to this one here. So this is my second order, same exact thing, right? So I'll leave it on this slide. You can see that these are all of the different models that the students are able to come up with. And hopefully by the end of the semester, they at least have a better understanding of how they develop them. So thank you.
Thank you. Any questions for Heather? I have one quick question before we translate to another speaker. So do students collect data and validate their things through this modeling, or?
Yeah, so I mean, it's a traditional class, so we do a lot of the traditional things of, they have homework assignments and stuff. But we also do a lab. So I have them do a lab where they look at spring mass damper systems, and they can collect data on that, and then they can compare that with what their modeled estimation is. They also do design projects where they have to design, something to meet some criteria. And so they have to take these ideas and now apply them to a real world example. So there's, more of the, this type of problem solving, like basically engineering design, is kind of a bigger part of it. So we do also have in our program a dynamics lab. And so in that lab class, they would actually get more experience with seeing these types of systems and understanding how they behave.
Wonderful. Thank you, Heather. Let's thank Heather for the presentation.